I'm going to first let fz, the function fz represents this polynomial that is given. So it is z to the power of 4 minus 2z to the power of 3 plus az square minus 8z plus 4t. And since we are given that bi here is the root of this polynomial, that means f bi, this must be equal to 0, which means that we have a bi to the power of 4 minus 2 bi to the power of 3 plus a bi to the power of 2 minus 8z, z is bi, so minus 8 bi plus 40, this is equal to 0. And I'm going to expand whatever that is on the left hand side and regroup them into the real plus I imaginary. So here we have b to the power of 4, I to the power of 4, and I to the power of 4 is positive 1. So this is going to be b to the power of 4. And here we have a b to the power of 3, I to the power of 3. I to the power of 3 is minus I. So this will become plus 2b to the power of 3, I. And here, b square, I square is minus 1. So minus ab square. Then here is minus 8bi plus 40. This is equal to 0. Grouping all the reals together, we have b to the power of 4. This is the real portion. Minus ab square. This is the real portion. And there's one more, which is this 40. And the part that is imaginary will be this 2b to the power of 3 minus 8b. This is equal to 0, which we can also see this as 0 plus 0i. So we can match the real to the real and then the imaginary to the imaginary. So let's do that, and I'm going to start with the imaginary first, because by doing the imaginary to imaginary, we will get an equation in terms of just b. So it is 2b to the power of 3 minus 8b. This is going to be equal to 0. And since the question says that b is a positive real number, so if b is a positive constant, that means b will not be equal to 0. So we can safely divide throughout by 2b. Let's go for it. Let's divide this throughout by 2b. So it is going to be b to the power of 2 minus 4. This is equal to 0. And we can do this because b is not equal to 0, which means that b is equal to, b squared is going to be equal to 4. This tells me that b is supposed to be plus or minus 2. But because b is a positive constant, so I'm going to go for just a plus 2. This is because b is a positive constant. So we have solved for b. Let's try to solve for a. So I'm going to substitute this back into here. So using this, it is going to be 2 to the power of 4 minus a times of 2 to the power of 2 plus 40. This is equal to 0. This can help us to solve for a here is going to be equal to 14. And now we know what is fz. Fz is going to be z to the power of 4 minus 2z cubed. A is 14, so plus 14z square minus 8z plus 40. In the equation, this is going to be equated to 0. And how do you think we can solve this in the fastest possible manner? We will just press this into the calculator. Let me show you what I have from my calculator. So from my calculator, I will be getting this. Okay, so I've gotten this from my calculator. And since one of the roots is bi, and bi is actually this thing here. Bi is this. Okay, because this represents 0 plus 2i, which is the bi. So what are the other roots? The other roots will be this, and this. So this will be my answer. What are the other roots? So the other roots that the question is asking for will be 1 plus 3i, then 1 minus 3i, and we have a 2 minus 2i. That's my answer. We're going to make use of the previous part to solve this new polynomial. And if you can observe together with me, this is 40 and this is 40, but here is minus 8z, but here we have a 8w, positive 8w. So what if we were to change this to minus 8 and minus w? Then it is going to synchronize, which means that if I can try the same thing to the next term here, if I were to replace this z by minus w, we will have a minus w square, which will become aw squared. So it's synchronized to this. If I were to replace this by, once again, minus w to the power of 3, so minus w to the power of 3 is going to be minus w to the power of 3. So minus minus becomes plus. It is going to become this. Similarly, for this z, if I were to replace it by minus w, and to the power of 4, it will become w to the power of 4. So this equation here can be re-expressed as this. And if you were to now compare this to what we have previously, all the z will be replaced by minus w. And that's how I'm going to make use of the roots from the previous part to solve for this equation, which is going to be minus w is going to have values that is 1 minus 3i from the previous part, 1 plus 3i minus 2i or 2i, which means that the roots of this w will be, bring the negative 1 over to the other side, minus 1 plus 3i. This is the first root. The second root will be minus 1 minus 3i. Third root will be 2i. And the last root will be minus 2i. In B, we are given the complex number w, and this is in the Cartesian form, minus 6 plus 2 square root of 3i. So we are going to find first the modulus of w, which is going to be square root of minus 6 square plus 2 square root of 3 square. And this is square root of 48, which is 16 times 3. So this is 4 square root of 3. And as for the argument, let's first do a quick sketch of the representation of this complex number on an Argand diagram. It is going to be represented by this point. If I were to draw the basic triangle, here it is going to be minus 6. Here is going to be 2 square root of 3. And the argument is going to be this angle here. So based on what I can visualize on an Argand diagram, the argument of w is going to be equal to pi minus away the basic angle, which is this. And this angle is tangent inverse of 2 square root of 3 over 6. So this is equal to pi minus tangent inverse of square root of 3 over 3, which is 1 over square root of 3. So we will have a special angle here, and it is going to be pi minus pi over 6. So the argument is going to be 5 pi over 6, which means that w, when I express it in the Euler form, in the modulus argument form, which is what the question wants, it is going to be equal to, this is going to be equal to the modulus e to the power of I 5 pi over 6, and finally w to the power of n in the modulus argument form, it will be this 4 square root of 3 e to the power of I 5 pi over 6 to the power of n, which is equal to 4 square root of 3 to the power of n, then e to the power of I n pi 5n pi over 6. In B part 2, we are looking at w to the power of n, which we have derived from the previous part, and we are looking at w conjugate. For w conjugate, it is going to be sharing the same modulus as w, so it is going to be 4 square root of 3, and the argument is going to be negative of the argument of w, so it's minus I 5 pi over 6. And if we were to go for w to the power of n multiplied by w conjugate, it is going to be these two being multiplied together. So it will be a 4 square root of 3 to the power of n, e to the power of I, n pi over 6. It will be this multiplied by 4 square root of 3, e to the power of minus I, this. So this multiplied by this, if I were to multiply this and this together, we will get a 4 square root of 3 to the power of n plus 1. And this being multiplied together, we will have e to the power of I 5 and 5 pi. 5 pi over 6 of n minus 1 if we were to factorize out 5 pi over 6 for the indices. So for the index, so we will have this, and I'm going to express this into the Cartesian form or the trigonometric form. It will be 4 square root of 3 to the power of n plus 1. Then this is going to be cosine of 5 pi over 6 n minus 1, then plus I sine of 5 pi over 6 n minus 1. So if I were to look at it this way, now it is in the Cartesian form, and the question says that this complex number is purely imaginary, which means that the real portion, which is this multiplied by this, should be equal to 0, so that it can be a purely imaginary kind of complex number. So I'm going to let the real portion of w to the power of n w conjugate, I'm going to let the real portion of this be equal to 0. So let's extract out the real portion, which is 4 square root of 3 to the power of n plus 1. Then cosine of 5 pi over 6 n minus 1. So this is equal to 0, which means that it is going to be just simply this cosine of 5 pi over 6 n minus 1. So it is just going to be this to be equal to 0, because this is going to be positive all the time. So when this is equal to 0, I'm going to make use of the formula that I've suggested in the theory outline on the Achevas TV, which means that this angle here, 5, if I were to make use of that from the Achevas TV, 5n minus 1, this is going to be an odd number. So 2k plus 1 will represent an odd number multiplied by pi over 2, where k that I've introduced here is an integer value. Let's make n the subject. Making n the subject, n is going to be equal to, I will have a 2k plus 1. 6 multiply over, I will have a pi over 3 pi. Then divided by 5, divided by 5 pi, we will have a 3 over 5. Then 1, if I were to bring it over, it is going to be this. So n is equal to this, and we are looking at the smallest positive integer value for n. So to quickly find different values of n where k is an integer value, I can actually press this into the calculator, and let me show you what I've gotten from my calculator. I've gotten this. Okay, so if I were to press this into the calculator, if I were to press this as 2x plus 1 multiplied by 3 over 5 plus 1, and then generating a table, this table will show me all the possible values of n when k are integer values, -3, -2, -1. So this represents k. And if you were to look at this, I just need to extract out integer values. So integer values will be like -2, will be like 4 over here, it will be 10. The other number is going to be equal to 16. So if I were to just write it down from my calculator, n will take up numbers like -2, like 4, like 10, 16, and so on. So we want the two smallest positive integer values for n. So the smallest positive integer values for n, smallest, let me just write it as smallest n, okay? So the two smallest, okay, I better write. So it is going to be 2 of the smallest n is going to be equal, they are going to be equal to 4, and the other one is going to be equal to 10. These are the two smallest positive integer values for n.